I know it sounds terrible now. I'm sure you're not going to record anymore EEG. So the grounding of these devices is actually something that is not trivial, and that's what it protects the participants. So I'm not going into the details of these things, nor multi-channel device and things. I just want to briefly talk about the EEG. So EEG stands for electroencephalogram, and funny bit is that the guy that discovered EEG discovered it by chance. Well, it was not kind of really a chance, because this guy was fascinated by the activity of the brain, and he wanted to actually try to tie the electromagnetic activity of the human body with the brain as well, because ECG was discovered and characterized only something like 20 years before. So there was a lot of, there were ideas around the fact that organs and human body was working by means of electromagnetic charges. So what he did, he was plugging electrodes to his own very head, and I think his wife and dog heads, and to a radio amplifier, until one day he actually was able to record the EEG. Do you know why alpha wave are called alpha wave? Alpha is the first letter of the Greek alphabet. They are called alpha wave because it was the very first signal that he was able to say that's brain signal and nothing else. Alpha wave is very funny because in an awake adult, if the awake adult relaxes and closes the eyes, after 15, 20 seconds or a minute, depends on the previous state of excitation of the brain, the entire brain synchronizes to a specific rhythm that look like sine waves at a very specific frequency, which of course is slightly different for everybody, but the range is between 8 and 12 Hertz. And this pattern disappears almost instantly when the subject under recording opens the eyes. So basically performing this experiment in public, Hans Berger was able to show that's a brain signal, because if I close my eyes, after a while it appears. If I open my eyes, it disappears. And because he was able to show same behavior on multiple people, there was no doubt that that signal was brain related and not noise. And that's where it started. One thing is not exactly well understood, the phenomenon underlying the EEG. Because the human brain is so complex, and we can see and observe only a little part of the signals of the network. It's an extremely cumbersome network of neurons organized in layers and organized in types, with millions, billions of connections that they go through the big channel, which is the spinal cord and the 12 cranial nerves. So all those inputs, all those things, plus the direct sensory inputs of eyes and ears, which are the principal sensors of the brain, they are directly into the brain. The optical nerve goes directly into the brain. The acoustic nerve goes directly into the brain, while all other nerves and sensors on the skin, they have to travel to the spinal cord first. So it's not well understood exactly what is at the base of the EEG. We can only observe it. And some characteristics, waveform of the EEG, they have been characterized follow-up accidents or Yeah, most of the time is an accident. In a patient get an accident and a part of his head is damaged by a trauma, and suddenly the patient lose or has less control of a part of the body. That's how the cortex has been mapped originally. So anyway, there are three kinds of recordings from EEG. The spontaneous activity, of course, which is the one that goes continually on and is the one that is not well understood. And most importantly, we only record the most superficial part of the EEG. We have no clue of little clue of what's happening below the layer of the cortex, because that signal doesn't come out. Then the evoked potential, which are probably one of the most fascinating recording that you can make on a human head. You give some stimuli, and you can actually observe some interesting responses in specific areas of the brain. For example, you flashes in front of the eye, even if the eyes are closed, and you can actually see in a range between 100 and 300 milliseconds after some processing happening in well-defined area of the brain. And of course, you could think of going with needle electrodes, and you actually might do it in neuroscience. This is done all the time. That brain of rats and mice is sliced, and single cell they get probed with pipette or needle electrodes. How EEG is recorded? EEG is recorded by means of a standardized mapping of the head. The most common way uses 19 electrodes. It's called a 10-20 system. It's called a 10-20 because the head is measured across inion to nascion and across the two temporal prominences. And those dimension, they get divided in percentages of 10% and 20%. That's the name 10-20. There are denser systems called the 10-10, the 10-5, the 5-10, or the 5-5, where obviously those dimensions, they are divided by 5% or 10% or even less. And as you may understand, they use lots and lots of electrodes. Obviously, the finer is this grid, because the smaller are these percentages, the bigger the number of electrodes is, because the bigger the number of intersections of the grids is going to be. So CZ, these electrodes, numbering and names, they come from the lobe of the brain that they folds up to. For example, the electrodes with named F, they sit on the frontal lobe of the brain. The electrodes called C, they are right on the top of the sensory motor cortex area. So can you believe it that the entire body is actually corresponded to a very teeny tiny slice of the brain, which is about 1 to 2 centimeters wide and lies between C3, CZ, and C4 and no more. Everything else does other things. Well, the occipital cortex over here is the one that receives the eyes, and the temporal lobe is what it receives the ears. So we know those parts, what they do. Very little is known about the frontal lobe of the brain. And you might have read interesting story about lobotomy performed through the nose. There was a pretty kind of a nasty fashion a few years ago. This is an example of 10-10 recording. Well, standard. And those are the EEG signals. So the volume conductor for EEG, that is pretty interesting, because according to the measurements you want to take, you might want to change the definition of the volume conductor for EEG, meaning that you want to assume one electrode or summation of electrodes as a neutral point for your measurements. For example, if you're doing evoked potential for visual cortex, you might want to record from O1 and O2 at the back of the head. Maybe this is better because in this system you have also OZ. And sometimes OZ or PZ or CZ, they are assumed as a reference for that specific measurement. Sometimes you might want to refer everything to the Z line. So you want to use all those electrodes as a reference because you want to assess differences between the two sides of the brain. So as you may understand, the number of measurements you can take, and because it's so complicated to prepare the head of a participant for EEG sometimes, you might want to have the freedom of changing the volume conductor or the definition of the volume conductor after the recording is made. In order to do that, most of the time, EEG recorders, they record the data raw with reference either to the so-called linked mastoid, so that you have electrodes at the side of the mastoid bones, and those are tied together and used as a reference, or to avoid artifacts due to the mastoid muscles, then you use the earlobes as a reference, or sometimes the right earlobe is used for protection, similar like the ECG, so that you have special electrodes that decrease the likelihood of leakage current going through the head of your patient. And you record everything with reference to the left earlobe. Or sometimes the 3 points, the 2 earlobes and the tip of the nose are used as a reference, or just the tip of the nose. In any case, those area, earlobes and tip of the nose, they don't carry any brain at all. They are on the head, so close enough to the area of interest to act as a reference, but they are far enough from the brain to don't carry any brain signals at all, or very little. That's why they're assumed as a reference. Once you record EEG with those neutral reference point, you have one individual signal for every individual electrode. And the signal name is also the electrode name. So if this is the system you use most of the time, which I think it is, when you see CZ, you know that signal refers to the signal recorded from CZ position minus your reference, which would be probably the 2 linked earlobes. Once you have the signals recorded, then you can do every kind of referencing you like. Most of the time, what people say is the most useful referencing is everything referred to CZ. But as I said, it really depends from the experiments you're performing. So say that, you can understand now what it meant by unipolar or bipolar EEG, where the unipolar is the one actually from the specific source, so that you actually take one electrodes and surrounding electrodes to create the neutral, and you just go and look at that specific signal, and so forth. So those are the rhythms that we already discussed them with the alpha wave between 8 and 13 Hertz. And while you're recording alpha wave, what you do, you can actually tell exactly when your participant is about to fall asleep. And that's one of the first things that they teach you when you assess brain signals, because you might want to avoid your participant to fall asleep. It's amazing with long experiments that the brain get very bored, even if it's a task. You're doing a task like pushing buttons and things, and you might think, how can you actually fall asleep? Part of the brain, starting from the occipital cortex, start to go into sleep mode. And you see the alpha wave changing into the so-called bursts of alpha wave. That you have a brief period, a few seconds of very large alpha wave, like this one, followed by nothing alpha wave and then alpha wave, and these things start at the occipital region, and then it takes over until they become this, which is light sleep. I've done some experiments with a brain-computer interface, which are very fast. Spider, what's that?
It's just a fly. It's like sitting. Oh, bird. Sorry, I really hate this.
So I've done some experiments where actually I've seen patients going into REM sleep during the experiment. It was pretty interesting to see if they were still able to control the device during light sleep or total relaxation. And once they were going to sleep, we were let them sleep for a few minutes and then wake them up. So some clinical use of EEG, like understanding how deep is the anesthesia. So have you ever heard about that fear of many patients undergoing surgeries, that they wake up during the surgery and they feel everything and then they can't communicate with the doctor that they are actually out of the anesthesia? Ever heard about this fear? It's a pretty common fear, particularly for people that undergo several surgeries. This kind of things now is kind of not justified, because in 90% of the procedure, EEG is monitored during anesthesia, and the amount of anesthetics given is correlated with the activation of the EEG due to the pain or due to stimuli during the procedure. So if they see that the number of events that reach the brain is too much, they give more anesthetic, mostly localized anesthetic. So that's the best way of assessing how deep and how efficient is the anesthesia without having to guess or giving too much anesthesia. I'm not going into the details of this because I think we stress these things quite a lot. One thing that I want to mention, because you have a big number of electrodes during EEG, never ever skip the step of checking the contact impedance. Recommendation says that all the electrodes should be below 5 kilo, with the imbalance between them normally less than 1 kilo. Sometimes you don't see this number, but you see green, yellow, and red dots onto the screen. Green normally is good contact impedance, below 5 kilo. Yellow means it could be good, you don't know, but it may be that the average imbalance into the contact impedance of the yellow electrodes is more than 20%. In light of what we said before, that you have the amplifier, it is a voltmeter with an input impedance and variable impedances of all the channels, 20% imbalance is what it gives you the different heights of the EEG traces. Keeping them all grouped together, you make sure that they are affected by noise almost all the same way. And that's the reason why you should take care of this step of checking the impedance for the electrodes, going and fixing electrodes that are off the chart, because the ones that are off the chart at the beginning of the recording are the ones that more likely are going to jump up close to the edges of the dynamic range of the amplifier, and they are not going to work during the recording, giving you false results. So they might work very well at the beginning of the recording, even the red ones, but they might give you problem throughout the recording. So you're better off going and fixing them before that they become a problem for your recording. We discussed these things. So I'll just want to give a brief things about filters, very, very brief, I promise, because filters are the next step after the amplifier. Sometimes you don't see this. You see a flat line on zero. A flat line on zero on the visualization system, it could be that because you have a high pass filter, so you have capacitors, that they block this value and they want to put the signal back on the zero. But if the signal is already flat but not zero, well, it becomes zero. So that means zero, flat line, will means two things, actually three things. Your participant is dead. Which is very easy to verify, is not. The cable is completely disconnected, or the electrode is completely misplaced. You have this situation, but because of the filter you don't see it. So beware, because you are going to have a hardware filter and software filter. So you can change the frequency content of your signal by hardware and by software. Guess what? If you do it by hardware, you are stuck with it. If you insert an high-pass filter into the hardware chain, which sometimes you can do, you're stuck with it forever. So all the recording you've done are with that filter. And if you process the data and you see lots of blanks, you don't know from where they come from. Software filter, sometimes they are just convenient for visualization at the moment, but you might want to use the raw signal screen to understand where they sit. Like in the case of the EEG, maybe red dots, if you have the software filter on, the one that they scored red at the impedance checking, they're working fine. But that is because you are visualizing the signal after that it's been pulled down on zero, after that all this squaring of the signal has been smoothed by the filter, so it seems everything all right. All those things suddenly become known if you turn off the filters, the software filters, and you watch the raw data. And you understand why you need to fix things before the problems are. So filters are important. So if you want to have a very quick understanding of how filter works, there's a YouTube clip down here that you can go and watch it. There are tricks that as engineer we like to use to fuse together amplifiers and filter. I'm not going to delve into details of this thing. There are even tricks to actually filter raw data without destroying filters or putting capacitors in between the signal pathway like this one, but once again I'm not going to delve into details. You have the slides if you like. That's what I was discussing before. About software filter, there are some interesting facts about filters, particularly distinguish between FIR and IRR filters. Those two brief video, they will give you an idea of what those filters are and what they can do and what they can actually make you think you're doing, like you have a good signal but you actually have not. But most importantly, filters, they are designed to shape the frequency content of your signal, removing noise out of your signal, particularly power line noise, high pass, low frequency noise from electrodes, and high frequency noise from movements and other artifacts. This means that if you want to understand the filter, you need to be familiar with the Fourier domain or the frequency domain, which is something quite difficult to grasp if you have never done it. I'm not the right person to explain these things briefly and in a way that everybody can understand. However, in my quest for this concept for audits that are not engineering, I found this video on YouTube, which, if I remember correctly, in only 45 minutes explain everything without nominating nothing out of the typical engineering or physics jargon where I'm going to fall if I try to explain to you. So it is very interesting and it might give you an understanding of what the filter they do, so that you can understand what is happening when you actually turn on a filter. Because remember, every time you turn on a filter to clean a noise out of your signal, you are actually inducing a noise on your own, no matter what. There's only one filter that does not induce noise on your signal. First of all, it is a software filter. Secondly, it is an IRR filter. And thirdly, is applied on the signal, going on the signal to the direction of time and coming back on time. It's a very complicated filter and is a concept that might seem awkward to grasp, but that's the only kind of filter that reduces the possibility that you're actually interpreting something that is not. Okay? So think about it when you have all the dials of the filters, particularly with the high pass filter for EEG. Be very careful with the high pass filter for EEG. So low pass, you can keep the low pass of the EEG at 30 Hz with no problems, unless you're doing evoked potential. For evoked potential, you want to see the sharp, steep going of the evoked potential, because evoked potential, particularly the P100, does like this. That's P100 most of the time, positive peak 100. Then you're going to have a negative 200, and then most of the time you have a large P300, followed by sometimes a N400 and a P500, and sometimes you even have a N700, depending on the kind of evoked response. This is very sharp and steep. If you filter your signal at 30 Hz, you might miss this altogether. Learn it on my skin. Electrical safety, that's we discussed a little bit of these things. Noise capture, we discussed this. Noise and interference, particularly from the cables, when you move the cables and everything. this is something that I mentioned, the reason why you have the cables all coiled together coming from the ceiling in EEG is because every time you have a conductive surface and you swing it into the air, you're gonna catch electromagnetic noise into that surface. The smaller the surface, the less likelihood of catching noise. That's why cables are twisted together, wired together. Sometimes you have record noise on the EEG. What you can do, you just go reach your participant and make sure that the cables are not touching like the metal chair or the skin of the subject, or that they are properly twisted together. And sometimes you go and touch the hand on the left side of your participant, and if you see a reduction into the noise capture, it means that there is a problem with the right leg driver. So you just go and fix the earlobes. And that's it. Questions?